Okay, I think we'll get started. So we've been talking about adsorption at the molecular level with molecules coming onto the sites to occupy them with in the context of the Langmuir model. Well, now we're going to back out of this and look a little bit more macroscopically and talk about the phenomenon of wetting and talk a little bit about the thermodynamics of that, and also do just a little bit of geometry. So it can be a rather complicated geometry. All right, so you might well be familiar with if a little drop of water falls on, say, your window versus or a countertop versus, say, some waxed surface, the nature at which it beads up on that surface is different. And that depends on the characteristics of the water or any other fluid and the characteristics of the surface that it's trying to wet. And so when some fluid comes in contact with the surface, and usually we're talking here about a small droplet on the surface, we can make some measurements. And the most important of which is something called the contact angle. So if we look side on this droplet that's sitting on a surface, we can measure the angle at which the tangent angle to the curve of the liquid right as it contacts the surface. And that's called the contact angle. And then we can express the various properties of this adhesion to the surface versus cohesion among the molecules to try to keep it together as a droplet. We can express that in terms of some of the thermodynamic properties of this. So let's see how that goes. All right, so we can talk about the extent of wetting. So we say, how much does it wet the surface is usually what we say. And this is a balance between the adhesive forces between the liquid and the liquid molecules and the surface, and the cohesive forces amongst the liquid, as I was mentioning. Now, in terms of the contact angle, if we have a contact angle of 0, then we have complete wetting. So this would be an ideal case where the liquid just spreads out evenly across the whole surface and there's 0 contact angle. Any real liquid is going to have some kind of contact angle. If that's less than 90 degrees, so if this is coming in less than 90, kind of like what I have drawn here, then we say it's partially wetting the surface. And that's on a gradient, so if it's very small angle, then it's really wetting the surface quite well. If it's getting close to 90, then it's just barely wetting the surface. And then if we have an angle that's greater than 90, so that's going to look something like this. The liquid beads up on that surface, and we say that it's non-wetting. So that does not wet the surface. So this would be an example of, say, a waxed surface, and water would do something like this. Okay, well, other things can affect the surface. We're going to be thinking about just a perfectly pristine, clean, smooth surface, but roughness can matter, and the chemistry, the actual chemistry of the circuit of the surface, and that does get into adhesive, but other chemistries that might be happening, and then charge, if the surface is charged. So these are some other complicating factors that might be involved, but we're not going to worry about those today. All right, well, there are a couple of important equations that that are associated with wetting, and let's kind of see where these come from. So there's something called the Young's equation, and let's see what we've got here. We've got the surface tension of the solid and the vapor, and this is one that for me, it's hard to think about why this would matter, because it's not where the drop is, but we're trying to wet the surface, right? And so before the wetting, the interface was solid vapor or solid gas, and now it isn't. So that's why this is also involved in the wetting process, because we're always comparing against when it's not wet versus wet. and we do need to include this. This is an important factor. Then the surface tension between the solid and the liquid. Of course, we would expect that to be there. And then finally, the surface tension between the liquid and the vapor. So how much is that wanting to keep that liquid from stretching out that surface? So these are all going to be involved. And so let's see how this plays itself out in terms of the surface tension along the surface here, because we're interested in the wetting surface. So we can imagine that these are opposing, and that's what we see here. So this and this, so we get a relationship here in which we're subtracting one from the other. And then we've got the liquid vapor pulling on this, but it's going to be impacted by the angle. And so if the angle was 0, then this would become cosine of 0, which is 1. And the difference between the surface tension, surface versus vapor, surface versus liquid, then would be equal to the liquid vapor surface tension. But as this becomes, say, up to 90, then this would go to 0. And then the tension, this is coming in at a straight 90-degree angle, so then the surface tension vapor surface and vapor liquid and surface liquid would be equal to 0. Now, when it comes to the work done, we have what's called the Dupre equation, and what we're focusing on here when we say the area, we're talking about the area that's being wetted. So you imagine this drop, that area is going to be a disc on the surface. That's what we're talking about when we say area. There are a lot of areas here. There's like the surface area of the capped sphere that we might be thinking about as well. But what we're talking about here, when we do the thermodynamics of this, is we're talking about the area that's being wetted. So we might say there's a 1 square centimeter area being wetted, for example. That's the surface. So that's our dA, and that's the generalized displacement. So we have the work here is going to be cast in terms of generalized force, generalized displacement, based on the surface tension. And so the Dupre equation says that the generalized force, the total generalized force, is coming in this way. The surface vapor minus the liquid surface, so that's kind of this bit, although we're not combining these equations yet, and then we're adding on this liquid vapor. And so this is the relationship that comes in for the work done for the adhesive part, the wetting, well, not the wetting part, the adhesive work that's happening. Now, there's other work that's happening. That's the work done to break the cohesive forces. So we're not wetting yet. We just have the adhesive part. Now we have to talk about the cohesive part. And what's done here is we imagine we're taking this sphere or this droplet, and then we're just going to cut a plane, right? And we cut this in half, and so essentially we've created twice that surface area, and so the amount of work is 2 times the liquid vapor surface area for cutting this drop in half, and that's the cohesive work. So we have 2 work terms, one for the adhesive, one for the cohesive, and we said that the extent of wetting is adhesive versus cohesive. So the total work then for wetting is defined as cohesive minus adhesive, and so we can just plug these values in. So we have our dA coming along, and then we have the 2 liquid vapor then minus this. So this comes in minus, minus, plus. And then we can do some cancellation. So we can cancel one of those. And we're left with this. Okay. Now what we can notice here is with the Young equation, we can switch out the surface vapor and the surface liquid in favor of the liquid vapor, because that's going to be more easily measured. There's bigger tables of the liquid vapor surface tension, because here, in both of these cases, it matters what the surface is. Well, I guess here, it matters what the surface is and what the liquid is. So there'll be it's water and this, or hexanol and this. Here, we would just look up the surface tension of the given liquid, because that's considered to be liquid air. Okay, so we want to cast the work in terms of this more easily measurable, or easily something you can look up easy, surface tension. And so we can use the Young equation in here to substitute, and we can substitute this in here for that. Now we can pull out a common liquid vapor surface tension. So the regular, if you Google the surface tension of a liquid, that's what that would be referring to. And then the area again of what's being wetted. Okay, so this is for an infinitesimal amount of wetting surface. So let's take that from 0 out to the size of the area that we are wetting, and let's do that reversibly. So just infinitesimally slowly, we wet that surface. Then we have talked about the fact that the Gibbs free energy is the non-pressure volume reversible work, or maximum work. It's the energy available to do non-pressure volume work. So that's going to be the maximum work. And so we simply integrate this up to the full area, and we get an expression here now for delta G of wetting. Now we're going to just kind of stop here in terms of the thermodynamics, but we could do this at standard temperature or standard conditions. And have standard conditions here. Then we could talk about well, even not even under standard conditions, we could talk about delta G equals delta H minus T delta S, and we could start talking about the enthalpy of wetting, and we could talk about the entropy of wetting. We're going to leave that for a later course in the curriculum. For now, we just want to get the idea of wetting down in this introductory course. Okay, so let's do an easy example. So let's say we want to wet a 1 square centimeter surface. This is a typical value for water and a typical contact angle for water on a particular surface. So just plug our numbers in. This is a typical, in SI units, we're newtons per meter. So here we were given this in millinewtons per meter. And so converting to newtons, and then converting the square centimeters to meters, and then this is unitless. So I think we end up with 4.3 times 10 to the minus 7 joules there. So you can just check that with your calculator. All right, let's get into some of the geometry here, because it's kind of interesting geometry. It's called spherical, well, not called, but it's the geometry of what's called a capped sphere. So if you lop off the sphere like we are here, can we express things like the area, the radius of the circle that it's casting on the cutting surface, which would be the wetting area in our case, and the height, contact angle, and everything. So let's first relate this contact angle to the angle that the radius makes from the center to where the surface intersects the sphere. So let's call that angle alpha. Well, we can see that if this is tangent, then this is a 90-degree angle here. And so our contact angle plus this angle here, we'll call that beta, is 90 degrees. Oops, so in other words, I had this wrong here. In other words, theta is 90 degrees minus beta. Now let's cast a line straight up like this, such that we intersect perpendicular to the surface. Then we can use the interior angles of a triangle being 180 degrees to get alpha in terms of beta. So alpha is 180 minus 90, because this is a 90 degree, minus beta. So 180 minus 90 is 90. So alpha is 90 degrees minus beta. So this angle alpha and this angle theta are the same. So when we can cast, if formula which are normally cast in terms of this angle alpha can be cast in terms of this angle, which would be related to the physical angle of the contact angle. All right, a couple of other things. The area is pi a squared, because a would be the radius of the disk that's cutting through the sphere here. A is going to be r sine theta. And then h is a little more complicated here, but we have to just do some trigonometry. I won't go through all of it, but we can cast h in terms of a. So if you want to do it on your own, you might want to cast, let's see, r minus h, do some trigonometry here, cosine, and then work yourself backwards and try to recover that formula. There are three different ways we can cast, well, three common ways to cast the volume, and it depends on which is more convenient. And so I've just listed these here. We can cast the volume in terms of A and H, which might be a good thing to do for wetting. We can cast in terms of R and H, which is probably less useful for wetting, because we're not directly measuring the radius of the sphere, which is R. We can cast in terms of angle in R. Angle is nice because it would be the contact angle, but then we have R here. So what we're going to do actually is take this formula and cast it in terms of A, so that we have A and the contact angle. So by substituting this into here, R is A over sine theta, so we get A cubed over sine theta cubed, and then we carry along the angle formula. So this is a nice formula for wetting because it has A and contact angle. So let's just do a very quick example. Let's say we've got, we want to wet an area of 1 square centimeter, and with a wetting angle of 20 degrees. Let's get some of the parameters then. So the wetting area is going to be, which I guess we've been using this fancy A when it came to the physics of it, is going to be pretty simple formula, and we can get that in square meters. R likewise, just 1 over A, and then, A, sine over A over sine, A over sine. And then the height formula, plug that in, we get 0.17 centimeters here. So this is definitely not drawn to scale. That's much more than 20 degrees. So we'd be looking more at something like that maybe. And so definitely we would expect the height to be much less than the area, which is what we've calculated here. Then finally the volume of the liquid in that wetting drop. this should be meters cubed. So again, a complicated formula, but you can carefully work that out and check those numbers. All right, so this is just a very brief introduction to the idea of wetting. We will likely come back to this, well, we'll certainly come back to this later on in the curriculum, where we can get into a little bit more of the thermodynamics that are involved, and also see the relationship between this and interfaces. Valuable to think about some of the stuff that we've been talking about, and it's a good chance to see where we go from the molecular level with Langmuir model up to more of this thermodynamic level here with the wetting.